Hey everyone, in this video we're going to talk about the process called glycogen synthesis or glycogen biosynthesis. And just to remind everyone, glycogen is the polymeric form of glucose that represents sort of the storage form of glucose in cells. It's an insoluble form and it's mainly found in mammalian systems in the liver and also in muscle tissue. So there are three steps that will convert the molecule glucose ultimately into glycogen. And actually, this is going to start with glucose 6-phosphate. So let's look at the steps here. So we have glucose 6-phosphate. I'm going to go ahead and just draw out the structure here. Oops. Let me erase that. I'll do a Howarth projection here of glucose 6-phosphate. And I'm just going to abbreviate my phosphate with a circle P there. Obviously, you guys all know that that's actually a phosphorus with several oxygens around it. So this is G6P. So when cells get signals that basically say there's a tremendous amount of glucose already present, and maybe the cell already has a lot of ATP present, the cell, again, is very greedy. It doesn't want to lose its glucose. So instead, it's going to now shunt this into an insoluble polymer form as a storage mechanism. So glucose 6-phosphate first is going to be converted into glucose 1-phosphate. Let me finish out that one. OK, so what's going to happen here is the phosphate from the 6 position is going to be hydrolyzed off and moved over and stuck on to this position. And this time I actually am going to draw out the phosphate. I notice I messed up on this. Let me redraw that part right there. So this will be converted to that. There we go. All right, so again, just numbering our carbons, 1, 2, 3, 4, 5, and 6. So this phosphate on the 6 position is hydrolyzed off, and then the same enzyme is going to flip this molecule over and stick the same phosphate onto the 1 position. So here you have 1, 2, 3, 4, 5, and 6. So the 6 is a free hydroxyl now, and we now have the phosphate on the 1 position. The enzyme that does this is actually called phosphoglucomutase. So we now have G1P. So that's step number 1. OK, the second step of glycogen synthesis is going to be sort of the activation of this molecule. And in order to activate this, the molecule UTP, uridine triphosphate, is going to be used. So I'm going to draw the phosphates out of UTP like this. So this is like ATP, but it's got a uridine attached to it. And what will happen in this next step is the activation process. So what's going to happen is glucose 1-phosphate is going to react with the alpha phosphate of UTP. Recall that the phosphates are labeled as such, so the one that's closest to the sugar is called the alpha, the one in the middle is the beta, and the terminal one is the gamma. And so what this will now create is a molecule called UDP glucose. Let's draw that out. And I'll just abbreviate my phosphates like that. I have OHs down here. This is a ribose sugar. And the rest of my glucose is the same. We have something like that. So this is now called UDP glucose. So in order to activate glucose 6-phosphate into this molecule, it does take an equivalent of energy. So UTP, we're hydrolyzing one of these high-energy phosphates, is essentially energetically equivalent to an ATP. So it does take some energy to activate this into this molecule. This is essentially the committed step of glycogen synthesis. And this enzyme is called UDP glucose synthase. Okay, not surprisingly. And that is a major control point. If that enzyme is turned off, it will essentially prevent glucose from being shunted towards glycogen. All right, so that's steps 1 and 2. On the next section here, I'll just show the very last step. All right, so in the very last step of glycogen synthesis, what will happen is that activated molecule of UDP glucose is now going to get added on to a growing glycogen chain. So glycogen, again, is this polymeric form of glucose. It can have alpha 1,4 linkages or alpha 1,6 linkages in its polymer. And glycogens can grow several hundred to even several thousand glucose units sort of linked together. So what I'm going to do just schematically here is just show, here I have glycogen within number of subunits. What will happen is the enzyme glycogen synthase will catalyze the following coupling. What's going to happen is the UDP molecule is going to fall off, and the glycogen chain is now going to add at this position. But notice it's going to add in an alpha direction. So what actually is happening in the enzyme, and I won't worry too much about the mechanism, but what's happening is the ring is actually popping the UDP glucose off to form what's called an oxocarbenium ion intermediate. It would look like this. That's a plus charge. And then that intermediate, that high energy transition state, glycogen will then come in and add to that. All right, so the resulting product then is going to be glycogen with N plus 1 subunits. So we've added now on this next glucose. The process could then continue again. Glycogen synthase will act again. And so then the byproduct here is UDP. Notice UDP is coming off. So that pathway now, the complete synthesis of glycogen, again, was 3 steps. First, it involved the conversion of glucose 6-phosphate to glucose 1-phosphate. That was by that mutase enzyme. Then this high-energy UDP glucose was synthesized as a second intermediate. And then lastly, glycogen synthase, which is also a heavily regulated enzyme, will then add this UDP glucose onto the growing chain of glycogen. All right, so that summarizes glycogen synthesis. I hope that helps.